Hello everyone. I wanted to go over the addition rule in probability. So let's consider a Venn diagram. If this represents the sample space, every possible outcome of an experiment, let's consider A and B being two different events. A and B may overlap, they may not overlap. And the question is, what is the probability of A union B or A or B, since or and union are the same thing and an intersection are the same thing? Well, if I look at the picture, if I take the probability of A and I add it to the probability of B, I will double count the intersection. So the probability of the union is the sum of those probabilities minus the probability of the intersection. Generally speaking, if the intersection is empty, therefore having a probability of 0, then we'd say the two sets are disjoint and the two events are mutually exclusive. So disjoint and mutually exclusive are similar terms. Mutually exclusive applying to the events themselves. Now, I want to look at a very special case. I have event A in my sample space, and then I have everything else. So everything that's not in A, of course, would be therefore in A complement. And we know that A union A complement will be the entire sample space. A intersect A complement would be the empty set. So with that in mind, we can say that the probability of A plus the probability of A complement must equal the probability of the sample space, or 1. And that gives us then the probability of A is 1 minus the probability of A complement, which is a very powerful formula. It comes down to this. If calculating the probability of A is more difficult than calculating the probability of its complement, then you simply find the probability of its complement. And that leads to a really nice feature, and we call it the probability of at least 1. You want to do a repeated experiment where the probability does not change, something like flipping a coin over and over again, or playing a slot machine over and over again. And the probability of at least one occurrence of the event being successful. Well, if the complement of at least 1 is none, then the probability, if I said let's do this n times, n trials, then the probability of the probability of A being successful at least once in n trials would simply be 1 minus the probability of A complement occurring every time. I'll put all n times. So once again, saying at least one success, the complement is no successes. So the probability of at least one success would be 1 minus the probability of its complement. So let's look at a simple example of this. All right, suppose you're playing at a slot machine. And the probability of success, let's just say, is 1 in 1,000. That might actually be kind of generous. Now, since the slot machine starts over every single time, it doesn't remember a previous success or failure, so the probability remains 0.001 every time that you do it. So if I said you want to do this 300 times, and you want to find the probability of at least one success. Well, if I said, what's the probability that you lose 300 times in a row? If the probability of success is this, then the probability that you're going to lose would be this number. The probability you're going to lose 300 times in a row would be this raised to the 300th power. Therefore, the probability of at least one success would be 1 minus this, which would be approximately 0.2593. It might surprise you that it was actually that large.